Hello, so a bit of an update. I haven't updated that much, and said I was going to do the firmware, but I'm not doing it. So here I'm going to give you a tutorial instead on how to flash some LEDs with an AVR type microchip. So I've got the Atmel Explained Mini. This is based on the Atmega328p. And today, originally in my project, I said I'm going to use STM32, but it's because I am so noob, I guess, at firmware programming or just programming in general. I have to baby it down and start from somewhere. Well, everyone starts from somewhere. So here we go. So I've got two buttons you cannot see, but if I press the button on the right, LED moves to the right. If I press the button on the left, LED moves to the left. If I keep pressing the button on the right, it still stays on the furthest right LED. And once I press it to the left, it goes to the most left LED. So you see, interesting stuff. Very easy project. Easy if you're, well, I found this a bit troublesome actually because my brain didn't compute correctly. So how do we do this? I'm going to walk you through this. Of course, this is very basic firmware programming, but your code might look something like this or even much better. So I'm going to start off. We have the F CPU. From what I understand, this is the clock that you want to set your microcontroller. So I believe this is in hertz, so this is 1 megahertz. We have to include avr/io.h. This covers all the ports and things, so we don't need to mess around with that kind of thing. This file covers it all. We include the delay, so I think this allows us to use the delay function. And we have define some functions, not functions, some macros here. We have bit set, bit clear, bit flip, bit check. So to bit set, we select the port, the byte, and the bit. So an example of this would be here. So I want to set bit set port B LED 0. I have defined LED 0 as 0. So it would go to the port B register and the 0th bit, or the first bit, but you know what I mean, it goes 0, 1, 2, 3, 4, 5, 6, 7. So that will enable that because we are shifting one bit towards that location. This is an OR equal, so this is just logic. If it's OR, it's going to, if it gets a 1 either way, it's going to turn into a 1. If it's 1 and 1, you get still a 1. So if you just look up OR truth table, you'll understand what I mean. But this is essentially an OR gate. Bit clear. This is how we're going to clear bits. So for this case, I have 1 bit. So this is my LED. So notice when I click the left button here, we are setting only this bit and we have all these turned off. This is because we've cleared them. So we've cleared port B, LED 1, 2, and 3. Set those to 1, 2, and 3 respectively. Same thing again, it's port B, the first bit, second bit, third bit. We shift to 1 and we AND and negate that bit, we get a 0. And so if you look at the AND truth table, I believe we get a 1 when both A and B for our inputs are 1. So our input being the port, which is already, it could be a 0 or 1, and then we're shifting 1 bit to it. So if we get a 1 or a 0 AND gate, so if we have 1 and 1, an AND gate would produce a 1, and then the negation get a 0. So that's how it's clearing it. We just get the difference out of it. Bit flip, this is essentially, as the flip says, like we are just checking. Sorry, we are just reversing what it is. So if it's a 1, we get a 0. If it's 0, we get 1. Bit check, we are checking to see what bit we have, 1 or 0. It's just an AND. So those are macros that we have defined here. Again, they're just truth tables of logic gates. Search them up, you'll find them. We define the LEDs here. This is good practice as we can easily change whatever pin we want. Say we suddenly want to use, I don't know, pin 6 in port B for LED 0. And instead of searching through and changing, so imagine if I just had all this things to change, like here. So if I just put 6 here, if I had a 2 here and I want to change the text, I'll change this 4 times, but instead I can just change this once. Same goes for the buttons, left button, right button, and the position. I've put this LED position. Where is our LED going to be at? So this is just a integer, which can only be whole numbers. So first off, we will need to set the direction out of the LEDs. You'll find that in all programming, in whatever, in your microcontroller, there's different registers and you need to set usually the direction first, or you have to enable a clock, or you have to do something to lead to something else. In this case, we can set the direction to either input or output or whatever, depending on the register. So in DDRB, we could set the registers we set the registers as an output in DDRB. So these are just telling to these pins here, we want them as an output. And meanwhile in DDRD, we set these push buttons as an input. So you could see bit set, we are moving one, so one would be changing to put enabling the output, and bit clear. So if you find this register for DDRD, you find that 0 is what we need to make them an input. So coming through to the code, as you could see, we start off with our while loop. This means we will just continuously repeat what is inside here. We are then checking pin if bit check pin D PBL equals 0. So what does this mean? This means is our push button equal to 0? So I have these push buttons connected with a pull-up, so that makes them active high. I believe that's the correct term. So when they are not pressed, they are low. And when we press them, they turn high. And this has led to the change in our LED. When we press, we get high. And we don't press it, it is low. So when we press it, LED changes because it's registered as a high. No, it's sorry. So it's registered as a high. It's an active high. Right now, it is active high or LED. Or it is active high or push buttons because they have a pull-up connected to them. And when we connect them, when we press the push button, they turn low. So this is what our code is reading. Bit check pin D PBL. When it turns low, but a delay because it's debouncing it. It's a mechanical thing, so it's hitting it thousands of times really. It's not pushing it once and you get some noise in between. So it's going bum 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 bum. Then it's relaxing. It's also the reason why we have pull-ups and connecting things to pull down so we can ensure a known state. Because if you don't, you just get random, you don't know what state it is, and you can make false triggers essentially. So we do this, we check it again. Is it still low? Yes. We move our LED position minus because we press the left button. However, we only have 4 LEDs. What do we do? Well, if it goes from 0 minus 1, so this will negate it by 1, we will get minus 1. So this will be an error because we only have 4 LEDs. We haven't set anything. Okay, so we say if LED position is less than 0, so if it goes to minus 1, we set it back to 0. This is how we get a permanent state in the LED 0. No matter how many times I press it, it will still remain there. We do the same thing for the right button. Hopefully this is all making sense. We only have 4 LEDs. If it goes beyond 4, we want to move it back to LED position 3 because it goes 0, 1, 2, 3. No matter how many times I press it, remains at LED 3. How are we switching between these LEDs? This is where the switch statement comes in. So switch case, you easily Google this. This basically gives changes between a whole lot of different, you could put whatever you want in here essentially. And depending on this, I don't know what you even call this, but let's say it's this statement that you've put in, or this integer or whatever, you know, it's then switched in between, or this input. So this could be anything. This could be a user typed input or what. In this case, we have the LED position, and this is why we have the LED position here. If it's 0, we bit set LED 0, bit clear the rest. If our LED position is 1, bit clear LED 0, bit set LED 1, clear the rest, and so forth. And then we have to have a break after each one to stop it, essentially. And yes, this is the entire code. This could be a bit neater. For example, we could put all this in a header file. We could probably make this in a header file or whatever and have this very short enough. We could turn these into a function. So you could put the checking position, and we could only have like, essentially there's like, what, 2 lines of code, 3 lines of codes maybe, excluding the switch statements. But yes, but the goal is to try and get our main code as short as possible. So even this stuff, this could have been, I don't know, put somewhere else. But the goal is to have it short as possible, use as many functions, because what happens if we just keep it doing like this, and this is poor practice on my part, because I am still learning, so cut me some slack. If in the future we want to go back and change things, you know, we have to go through all these lines of code, and you know, maybe this grows into like 400 lines or whatever, going through each one. But if we have functions, we just go to the function, just change one, and every time we use that function, that will apply to the rest of the code. So you can see how convenient it is already, instead of each changing each one. Save yourself the hassle and also improve your code and portability and I don't know if portability is the right term, but flexibility maybe. But yes, that was a short tutorial of what I've learned recently anyway. I would like that to share it with you guys. The project wise, doing quite well. Well, I say quite well, I have to learn firmware. So it's a start, from somewhere. I'm learning this AVR because it is the easiest, and the STM32, I don't really know what I'm dealing with here. It's got its own unique things. So start off easy, do some easy projects, and we're going to slowly start building up towards which our goal is to use an STM32 for now.